This is again further we were discussing about the 800 kilovolts DC line, 1200 kV AC line. So, further in the country there is a thought where the HVDC lines for long distance transmission are much more economical and more power could be transferred going in for HVDC lines. So, it is thought by the utility and the government to further in case of large power transfer. So, going in for 1100 kilovolts UHVDC, ultra high voltage DC, could be much more economical and how beneficial to the country. So, for considering this point, a study has been conducted and research is in progress. Experimental have to be proved before actual commissioning of the 1100 kV towers on transmission UHV DC transmission. So, a brief idea what is thought which in case of 1100 kV UHV DC transmission is to be conducted, the benefits of going in for this. This shows the single line diagram of plus minus 1100 kV. The minimum total height of the tower has been shown around 64 meters, 63.5 meters is approximate estimated length, and several clearances, the minimum clearances from the metal to the conductor, all these are the indicative single line diagram. This is not yet being taken up in a full scale. So, preliminary design aspects are under progress by the government. Some information pertaining to this. So, the salient features going in for 1100 kV UHV line has been evolved based on the consideration some requirements. So, what are the basic requirements of a tower configuration? So, the basic suspension tower particularly for 1100 kV ultra high voltage DC transmission to be considered should be of a YY configuration similar to plus minus 800 kV which is being presently used. This will minimize the right of way requirement if we go in for this Y type of configurations. Second is insulation requirements, very important. The specific creepage per kilovolt for plus minus 1100 kV has to be considered same that of operating of plus minus 500 kV DC or plus minus 800 kV lines, which are under implemented like at different pollution zones, light, medium areas, which are normally assumed to be 41 to 45 mm per kV in case of medium or light pollution. Here the 67 insulators of 590 millimeter creepage are being used for a Y type of insulator strings for 800 kV. In case of 1100 you may have to use 93 numbers of insulators. So, the insulators number will increase, the clearances will increase. The pole to pole spacing for 800 kV is typically 22 meters which is being followed presently. If you go for 1100 kV the pole to pole will be approximately 28. So, several of these things have been are under study and estimated so that information is required in case if you go for 1100 kV. A lot of manufacturers have to come across in India. Again, manufacturing the equipment at this level is very, very important. So, further maybe a decade so 1100 kV HVDC line could be transmitting the power much more than the 6000 or 6500 megawatts which is being used by 800. This will definitely be much more helpful for transmission large chunks of power for long distances. So, what is the ground clearances in case of 800 kilovolts HVDC? We know that the minimum ground clearances is 18 meters and for 1100 kV it is estimated to be 26 meters. So, the factor of more than 8 meters have to be increased comparison from 800 kV DC to 1100 kV DC. So, lot of activity is being done. Then right of way, the minimum requirement for 800 kV is somewhere around 69 to 70 meters you can see here, but when you go for 1100 kV you have to be looking for a right of way somewhere around 93 meters. 93 meters is roughly around 280 to 290 feet, 300 feet roughly. So, it is a very high space which is required. So, several towers are likely to come, long distance, thousands of kilometers line, several aspects have to be considered before the final designs are to be cleared. So, right of way requirement will be 93 meters in lieu of 69 for 800 kV. The ground clearances will go high by 26, whereas for 800 kV it is 18 meters. So, this is again a typical similar thing which I have indicated, the same clearances tower. And what are the conductor surface gradients and corona onset gradients going in for 1100 kV UHVDC line, very important here. So, here various conductor bundles, the studies have been carried out with various conductor bundles using different configuration like hexa 6 bundle conductors of lap wing 38.05 dimensions. You see the maximum conductor surface gradients being 27.29 in corona onset gradient, that is kV per centimeter, 25.717 kV per centimeter for positive pole. Using the Moose conductor with octa, that is a 8 conductor bundle, you get 26.03 kV per centimeter, and going in for 8 conductor Bursimis you get 24, and going for octa, that is a 8 conductor lap wing conductors, you get 22.38, and going in for 10 conductor Moose bundle, that is a 10 conductor Moose bundle, you get 22.38. These are the estimated values for maximum surface gradient and corona onset gradients for 1100 kV. A lot of studies are in progress. So, similarly conductor current carrying capability and thermal rating for when you go for 1100, for that power rating you see at the maximum conductor temperature 75 degrees, in case if it goes to 85, 75 and 85, the thermal rating, the various conductors performance, you can see that for octa Bursimis these are the values, and lap wing 8 conductor, 10 conductor, these are the values which are being estimated. So, several information, lot of studies are being carried out to find out the feasibility for going in for 1100 kV UHVDC line in the country. So, if it is used, so then how the line losses, the conductor bundle for various configurations, the power flow using 8 conductor Bursimis conductor, what will be the peak line loss which is estimated kilowatt per kilometer. So, if the 1100 kV UHVDC line is being used with 8 conductor Bursimis and carries a power of 8000 megawatts. So, what will be the loss? 164 megawatts. In case of 8 conductor lap wing the loss will be 141, and in case of 10 conductor Moose the loss will be 173 megawatt, kilowatt per kilometer, loss will be kilowatt per kilometer. This is for transfer capability of 8000 megawatts. In case the power transmitted to be 10,000 megawatt, then the loss will be 259, 222 and 273 respectively kilowatt per kilometer for 3 different conductors. And if the conductor, if the transmission system is transmitting power of 12,000 megawatts, if the power flow is made to be 12,000 megawatts, the loss kilowatt per kilometer will be 377, 323 for lapping 8 conductors bundle, and 398 in case if we use the 10 conductor bundle of Moose conductor. So, this is how the estimation or a peak line loss estimation is being done for various power flow conditions. So, similarly audible noise and radio interference limits have been also estimated for 1100 kV. Here you again comparing with 8 conductor lap wing type of conductor arrangement which is 38.05 dimension, you see that audible noise the maximum estimated should not be increased 45 decibels, and at the edge of the right of way it should not increase more than 43 is the estimated value. And going in for hexa, that is a 6 bundle lap wing presently which is being used for 800 kV, the value is 41 and 39. So, a marginal increase has been seen by using the 8 conductor lapping conductor. So, this will again adhere to the international norms of not crossing the 60 microvolt or 60 decibel, sorry, 1000 microvolts or 60 decibel for radio interference. So, here you can see going in for octo lapping conductor less than 50 maximum of 50 decibels and 43 at the edge is being obtained, whereas for 800 kV presently it is 49 and 42 respectively. So, the line losses versus the line length for 1100 kV high voltage or ultra high voltage transmission estimated is shown here. As you very clearly see, this is the line length in kilometer and this is the percentage or peak line losses in percentage. This very clearly shows as the line length increases more than 2500 kilometers for various power ratings, the performance of the line is shown here for 12,000 megawatts, this being 8,000 megawatts, 6,000 and 10,000 megawatts, how the line losses are seen. This gives the line losses comparison for both 800 kV and 1100 kV DC. You can very clearly see for transmission of 6,000 megawatts, comparison between 800 and 1100 HVDC lines, very clearly this is the peak line losses which you see kilowatt per kilometer is y axis and x axis being power flow in megawatts. So, comparison, very clear comparison is shown here for 1100 and 800 kV. So, 800 kV the blue is for 800 and the red is for the 1100 kV. You can see the as the power rating of the transmission system goes higher and higher for 8000 kV, there will be a reduction in the peak line losses for various power transmission. For 6000 the values is 50% of the 800 kV. Similarly, it is 30 to 40% in case of 8000 megawatts and 10,000 you can see it is 30%, or in case of 12,000 megawatts you can see much more lesser than the line losses which are occurring at 800 kV HVDC line. So, this very clearly points out going in for long distance high voltage, a very high voltage DC line which will be much more economical to transfer a large amount of power for over a long distances. So, the power flow comparison per unit right of way gives an idea here for plus minus 800 kV ultra high voltage DC line and 1100 kV line. Right of way requirement will be 69 meters in case of 800 kV HVDC. In case of 1100 it is 93 meters, whereas the power flow in megawatts for 800 kV you can transmit anywhere around 6000 megawatts, and power flow per unit, that is a megawatts per meter, is 87, but for 1100 kV you can transmit up to 12,000 megawatts, that is very important. So, the double the power could be transmitted going in for 800 to 1100 kV HVDC. That is one of the major advantages, benefits for going in for higher UHV DC of 1100 kV, which is being presently thought, and the studies are being conducted. So, we were discussing about the various transmission aspects, high voltage AC, high voltage DC, which is more beneficial going in for DC for long distance transmission, how much is the power could be transmitted, several advantages of going in for HVDC, the tower, various tower configurations, various electrical clearances which are to be adopted for the various tower for ultra high voltage AC and DC aspects, and various types of conductors which are generally used for transmission, very high voltage AC and DC transmission. Several type of conductors have been discussed which are in use in the country, and the technology advancements particularly at very high voltages which is essential for the country have also been discussed. Now some important components, that is inspection tools for the high voltage transmission, like the conductors which are overhead conductors which are in the transmission towers. In case few of the strands are damaged, so the conductor becomes ages over a period of time and it requires the maintenance. So for such there are several tools have been developed, and at regular inspection or the hotline maintenance, these conductor issues have to be rectified for the smooth transmission of power. So for such recently equipment or the gadgets, one like the robot particularly for the inspection of transmission conductors or lines is being used both for electrical and mechanical related issues. Here this robot basically acts as a human machine interface. From the tower to tower, the robot is being used and it tries to identify the mechanical deformities or the conductors strands and the distances which the conductors are being placed, and it gives the information to the computer, where it could be very helpful in trying to rectify the damages which have occurred over the period on the conductors. So very important development which are being used. So the tests with cable spacers and obstacles in the lines are being rectified using these various gadgets which have been developed for the overhead transmission lines. Some of them are shown here. So this from tower to tower, these gadgets will be moved and the information will be connected over the PC, and this information will be given to take proper corrections in case the conductors are damaged or the spacer alignment or the spacer mechanically there are mechanically if the spacer is to be removed or it is to be replaced or the conductors have to be properly checked. So this will be very helpful. One such robot is again shown here for the very high transmission aspects, which has been recently developed and which is very useful for the transmission utility engineers to rectify the conductors, the spacing arrangements, the mechanical damages happen to the conductor or the spacers or to any other hardware component on the transmission towers. So this is how the robot is being used to see and check the status of the conductor, the healthiness of the conductor, and the information is being given to the utility engineers through the arrangement which a proper sensing mechanism, very useful for to find out the healthiness of the high voltage conductors. So that was about the various towers, the conductors, some advances which have happened and how the gadgets are helpful for the rectification of the conductors or hardware on the line, hotline maintenance aspects, several of these things. Some basic information about the tower foundation is also very important. So as I was mentioning, the towers are very important components apart from the conductors and the insulators. The foundation, again civil engineering aspect is very important for the long run, and this foundation play a very vital role for the towers to sustain for a period of the life of the tower, which includes several normal conditions, the conditions because of the natural calamities, the wind and several natural conditions the tower has to be able to sustain. So the classification of foundations, the tower foundations is of utmost importance, and these foundations which are to be carried out again depends upon several factors, and these foundations are classified based on the soil type and the subsoil content of water level which are generally listed here. So, in case of normal dry condition of the soil, the type of classification of foundations which are to be carried out. In case if it is the sandy type and a dry condition, what type of foundations have to be made for the tower. Again the tower foundations depends on the voltage level, the height of the tower, total steel structure, total mechanical load, wind consideration, insulators, conductors, several of these aspects have been considered. So, both mechanical, electrical clearances and also the civil engineering plays a dominant role for the transmission system. So, the foundation is a very important aspect. So, the conditions whether the soil is dry or wet or partially submerged with water or fully submerged in water, whether it is a black cotton type of soil or a dry fissured rock which is undercut type or wet fissured rock, or if the soil content is submerged fissured rock. So, is the place having a hard rock or a mountainous area. So, depending upon several of this classification, the foundations of towers are being considered, and for each aspect the suitable foundations have to be laid, so that the tower strength and the tower has to be working for the long period of its life. So, very important aspect. So, this classification of foundations play a role to suitably going for particular foundation for that area. So, unequal type of chimney foundations are also sometimes provided to minimize the benching and for waterlogged areas where the planar land or the area is not available. In such cases these chimney foundations are also provided for the construction of tower. How the design of foundations, again considering various aspects, following ultimate foundation loads which acts on the tower at the tower base along the tower slope are also considered, like the compression loads, there is a downward thrust which the tower sees, the uplift, that is a tension loading which comes to the tower, the transfer or transverse or a side movement or a thrust, then the longitudinal side thrust. Several of these aspects have to be considered apart from other dynamic changes which the tower sees. So, all this are to be considered for the design of the suitable foundation, which is very important for the tower. So, thank you. We have looked into the tower aspects and very briefly about the foundations which are essential for the UHV and ultra high voltage transmission system. We have discussed about the insulators, line conductors, importance of the towers, the clearances, electrical, mechanical clearances and the foundation aspects. So, we will further see about the aspects pertaining to the substation in the next class. Thank you.